Okay, so good morning, everyone. So if you didn't get your first quiz back or you're coming a little bit late, just see me at the end of class, and we'll get that returned to you. The scores are posted on Blackboard. Certainly, if you have any questions, please let me know. Either come to office hours, ask them at the beginning of the lecture. We're happy to get it addressed. So I guess before we get started, a few announcements. So remember, homework 2, we're going to finish that unit probably in about 10 minutes today. We'll be due Monday at the start of class, and we'll have our quiz on the data storage unit next Wednesday, so a week from today. We're going to start the third unit today, and that'll go through most of next week. And so sometime over the weekend, I will probably post that homework assignment. Again, it'll be due, I'll give you a week to work on it, but I'll get it posted probably before class on Monday. Does anybody have any general questions before we get started? Okay. Well, I put up the new sort of warm-up question for the new unit, but we need to go finish the old unit first. So let us go do that. So we finished off last time. Remember, we're thinking about this idea of data storage, of how do we turn all of these different quantities into sequences of ones and zeros. We spent an inordinate amount of time looking at non-negative numbers and how do binary numbers work. Okay? And then you're probably thinking we spent way too much time on that. But then once we had those, it was pretty straightforward to deal with negative integers. I left as an exercise for homework how to deal with rational numbers. And then immediately we moved into text. And how did we store text? How can we convert letters and alphabets to ones and zeros? Does anybody remember from last time? Yeah. Yeah, we can use a table. So there's a discrete number of letters and symbols or whatever it is that we're using for our text, and we can associate with each of them a particular non-negative integer. And so we saw like 32 meant space bar, as I recall, and 66 was somewhere in the capital letters, and there were things for all of the numbers, and there were things for all of your symbols like ats and greater thans and plus signs and semicolons and whatnot. But we could do that, and so we could take a letter, associate with each letter a unique non-negative integer, and then use our binary numbers to convert those non-negative integers to ones and zeros. And where we left off last time, sort of proceeding along, was the idea of looking at images. And so we saw that there are a couple challenges that we have to deal with when thinking about images that we didn't have when we were working with numbers or text. And in particular, that's the idea that there are lots of things in images that span an entire continuous spectrum. Okay? So we have certain things in images that we saw last time. How many positions do we have? If we were to hold up, pretend my orange folder here is some beautiful picture, how many different spots do we have all along that picture that we need to consider, that we might want to store the color at if we're going to put this on a computer? And in principle, they're an infinite number. Again, echoing from last time, can a computer process an infinite amount of information? No. So we have to discretize it up. And so what we can do is think about breaking that picture into maybe lots of vertical columns and lots of horizontal rows, get lots of little boxes all across that. Each box is called a pixel. I think we discussed that on the next slide. And what we're going to do is associate then what is the color associated with each pixel. And that's what the computer is actually storing. Likewise then, when we think about storing colors, how many possible colors are there that we could have at any particular pixel? There's an infinite number of colors. Computers can't process infinite information, and so we have to discretize our colors up as well. Okay, so we talked a little bit about discretization error last time. We don't need to go through it again. And to discuss sort of pixels and what the idea of these boxes are and how they give you resolution and all that, we spent a little bit of time looking at Super Mario through the ages as the different video game technologies and the different hardwares became more sophisticated from this image's perspective, starting from the Nintendo Entertainment System up to the Wii. Okay? Any questions on this example from last time? All right. Then if not, what I want to do then is to move on and think about how do we actually try to discretize color? And how can we do this? And so the idea is you could think about starting with some overall what's called a color space. So maybe over here on the left, we've got a whole bunch of colors. We've got some blues up in the top right, reds over on the left, greens in the bottom right. You can start to see maybe there's a little bit of yellow and orange here down in the bottom in sort of the middle area. It's black up in the top left and some teals and all that here in the center. In principle, are all of the colors that we sort of naturally think about in principle represented in that box? Yeah. Okay, so what ends up happening is what we're going to do is we're going to take this entire spectrum of all of these colors and we're going to basically discretize it and say, well, there's some countable number of colors we're actually going to consider. And so when we sort of block that up, maybe we use what's called a 128 color palette, which is to say of all of the possible colors in the universe that we could have, we're going to say we're only going to consider 128 of them. And I believe those are briefly pictured here in this middle palette here. So we see there's some reds on top, we've got some oranges, maybe some really dull golds, some greens, blues, and some purples. And when we then go and think about what are all of these colors we could have, what we can ask ourselves is which of those 128 colors that we're thinking about most closely resembles the color in that entire box. And so when we think about sort of breaking it up, you can see now where there's all of these discrete jumps around here, where say anything in this region here is best approximated by this one particular color from our 128-bit or 128 color palette. Okay, sort of think this is like a painter only has so many colors of paint that she can use. Okay, you can always mix more, you could buy more, fine, but suppose at the beginning you only have maybe 7 colors. When you need to paint something, well then which color do you choose? The one that approximates it the best. Okay, and that's what's going on. Okay, so the idea then, as we're thinking about this, just as we had with pixels, we saw on the last slide, as we introduced more and more and more pixels, could we get better and better and better images? Yes. If we introduce more and more and more colors, will we get better images? Do you think? Yeah, because there's going to be less approximation. If we add more colors, maybe we start breaking each of these cells into, let's say, either 2 or 3 or 4 parts, and all of a sudden there's less discretization error as we approximate the actual color that we need to store with a color that's available to us. Okay? The downside is the more colors we have, what happens? The more space it requires on the computer and the more processing power we're going to need to work with that image. So that's the trade-off. More colors means better images, but more colors means bigger images in terms of file size and longer times in terms of processing and displaying the images. And so the way that these work, how we can turn sort of these images into, or these colors into numbers. So we say, first of all, let's discretize all of those colors into some fixed number. And then what we can do is then associate some sort of number to each of those colors. So maybe if we go back to the last slide, think there's this sort of dark red here in the top left. Maybe that's color 1, and then color 2 is next to it, and color 3 next to it, and so on and so forth. Okay? And the way that this works generally is what's called a color space. And so there's a nice tutorial up there, and I grabbed one of the images from it, where basically one of the very common color spaces tries to quantify several different aspects of color in there. And so think about having now our normal sort of 3-dimensional Cartesian system. We discussed those back on the GPS unit. But now rather than one axis representing X and Y and Z, maybe one axis is going to represent how much blue or how much yellow we have. Okay, so if we're more on this side of the axis, we're a bluer color. And if we're on this side over here, we're more yellow. A second axis is going to be sort of red to green. And the third axis could be light to dark. Okay? And so by using then these coordinates to say, well, how much blue-yellow do we have? How much red-green do we have? How much light-dark do we have? We can start to describe a whole bunch of colors. And this is the idea of a color space. Okay? And so the way it works, there are several standard color spaces. The one that's pretty much used for a lot of things, unless you really need very, very high-quality colors and also like professional image development, is basically what's called the RGB standard. Anybody want to take a guess what RGB stands for? Red, green, and blue. And so what we're basically going to do is sort of now think about taking our 3 axes and making one of them how much red content do we have, one of them how much green content, and one of them how much blue content. And so we can form sort of that 3D cube where we can sort of say, where are we on that cube? Maybe we're white all the way on sort of the corner at the front. Black would be all the way at the corner in the back that's not actually shown on that cube. But we can have these 3 different axes to try to quantify how much red is there in our color, how much green is there in our color, how much blue is there in our color. And so there's a couple ways that these work that are given sort of, they're equivalent. The one that HTML usually uses, and you've got a homework problem working with this, is that we'll assign an integer 0 to 255 to each of those 3 directions. So we'll say our red content is anywhere between 0 to 255, where 0 means there's no red content, and 255 means it's completely saturated in red. Likewise, we'll have 0 to 255 in green content, and we'll have 0 to 255 in blue content. Okay? And that's how we can end up specifying this entire cube in all of these colors. So for just sort of a quick idea, how many different colors can be represented in this RGB color space? Anybody want to take a guess? Oh, how many different colors do we have along that red axis? Yep. Okay, where do you get 765? Okay, 255 times 3. Not quite, because that's now saying we've got 255 reds, 255 blues, and 255 greens. Is that all we have? No, because we've got, remember, this whole three-dimensional space. So we've actually got 255 cubed, exactly, because we can have any one of those 255 values along red, any one of those 255 values along green, and any one of those 256 values along blue, because 0 to 255 is 256, which, why did we pick 256? It's a power of 2. Okay? So it's 256 cubed, which turns out to be, what is that, 16,770,216 colors. So is that a lot of colors that we can represent in this sort of simple way? Yeah. And it turns out in most applications, that's sufficient. When you're looking at something on your screen, this is probably good enough. The human eye is going to fill in the difference. If there's any sort of approximation, or if there's any of this discretization error by sort of approximating the real color by one of these 16-odd million colors, you're probably not going to notice. And that was the idea. So there are plenty of websites that list RGB colors. Like I said, there's a lot of them that are standard in HTML. They've actually been given sort of names, so you can get black, white, red, lime, blue, yellow. So green is down here. We've got an olive color. And so what can end up happening then is they can then give sort of, here's the decimal code saying, okay, well, there's our R value. So like for black, R is 0, green is 0, blue is 0. For this blue color down here, notice red is 0, green is 0, but that blue is saturated at 255, telling us that's the most blue we can have. But there's no red or green in that color. What ends up happening then, the way HTML works to make this a little bit more compact, is it actually converts each of these R, G, and B numbers into hexadecimal. So think back, that's our base 16 that we saw last time. And so what it'll do is the first two digits of this are telling you what's that red number in base 16. The second two digits, what's the green number in base 16. And the third set of two digits, what's the blue content in base 16. And so we can use these number bases to go back and forth and see what's going on. And there are certainly, this website also gives a lot of less standard named colors. There's a really long list. Some of them have sort of entertaining names. You can find both tomato and bisque, not the same color, on there. Okay, so suppose now, again, we have these RGB values. They're just numbers. They're 0 to 255. HTML usually says represent them in hexadecimal. We could also represent them in binary. So suppose we have that our red component is 10110010. What color do you think that corresponds to? Or what's the red value in that color? Likewise, if G was 0010010, what's the content? So take a moment and think about that. And maybe while you're working, I'll start working on some of these here on the board. Yep, so it's in binary, we're doing base 2. So we have, the R is, remember, a lot of times it's convenient to start working at the right, because that rightmost digit in binary is always 2 to the 0, and sometimes it's easier to work from the right to figure out then what's the power of 2 that corresponds with that leftmost digit. Did I miss a power of 2 here? I did skip 8, thank you. I'm looking at this thinking it shouldn't be 256. Which one am I missing there? Thank you. I think that ends up coming out to be 178. Anyone else get that? Okay. And so we can go through and do sort of the same strategy. The green component works in the exact same way. The blue component works in the exact same way. And so sure enough, we can go look. Let me sort of clear this out a little bit. And so the color that this was actually specifying here was this fire brick, where if you convert it over, notice that the G and the B values are the same. They both come out to be 34. There was our 178 that we found for the red. And so if we ask what color is this, I don't know, according to this website, they call it fire brick. The numerical answer is probably also fine, unless it was explicitly asked what is the name of the color. Okay?
So like, if we got this on like a quiz, it'd be like, you want us to say fire brick, you want us to say like the color.
Well, if this is on a quiz, you probably wouldn't have the access to the website to actually get the name of the color. So you'd probably just leave it as the decimal, or whatever it was asked. It's possible I might give it to you in decimal and ask you, what is it in binary? Okay, so that's how, so thinking about back to images, we've now discussed how do we figure out pixels? How do we deal with the fact that we could have only a finite number of places to store along that entire canvas? And we've now discussed color spaces. How do we actually discretize the actual colors that we have to store at a given point? And so the way this all comes together is there are several standard image file types that then regulate to the machine how do we store, what's the number of pixels, how are the pixels laid out, and what is the color associated at each pixel. The most straightforward file format is called a bitmap. Has anybody heard of that or used bitmaps before? If you have, you know that they usually are very large in size. Okay? There are certainly other types of image formats. Has anybody seen or used a JPEG? Or a PNG, or an SVG, or a GIF? Okay, all of these are just different standards that the computer uses to say, okay, well now we have all of these ones and zeros, we know it's an image, but how do we turn those ones and zeros into either pixels, colors, or whatever? There's various encodings that are used. And so what ends up happening is the way a bitmap really works is it says, at the top of the file it says how many pixels do we have maybe horizontally, how many pixels do we have vertically, and then it just proceeds to list what is basically the RGB color at each of those pixels. I don't remember whether it's going across or going down, but it's going to go over every one of those pixels and say, here's the color at that pixel, here's the color at that pixel, here's the color at that pixel. It's a pretty straightforward one. Okay. Where this comes in is that some of the other file formats that are used, like JPEGs and GIFs, do things that are a little bit more sophisticated, where they try to figure out and do things a little bit more to say, how do we actually turn this more continuous image here sort of on the top into something discretized down on the bottom? Normally, what people might think is that a pixel just says, okay, well, here's our box. Look at the center of that box and say, what is the color at that point? And so maybe, you know, if we were to look in this box here, that would just be black, and we would assign the color black to that entire pixel. The problem is when we're working with sort of these discretized grids, if you've got this circular object and you don't necessarily have enough resolution to capture it. So see here, there's only 5 pixels across the top, around the bottom, or along the side. And when we have this circle, this sort of red line indicating sort of this curved shape up top, there really aren't enough boxes to capture that curve. And so what a lot of these more sophisticated images might do is try to do some sort of averaging over the pixel, where we would say, within this pixel, maybe, I don't know, 40% of it is outside the circle, but 60% is inside the circle, and it's going to try to weight those two colors together in a way to give you maybe a better representation of that curve surface. And then as you make the mesh finer and finer and introduce more pixels, we get a slightly better representation of that curve. But that's what some of the more sophisticated file formats are doing. But that's how, like bitmaps, JPEGs, GIFs, that's the general principle of how they work. Does that make sense? Okay. And so then if you're curious a little bit more about this and why we have all of these different standards, there's a classic article in the computer graphics community by Alvy Ray Smith. There's a link here, and it's pretty easy to read, basically going on and emphatically asserting that a pixel is not just a little square. And so what you can do and sort of see here is the same image. So we've got, I don't know, I'm guessing it's a parakeet of some sort. If anyone's a bird fan, you'll correct me later. And so we can take the same image and put it through different file standards to see what happens to the image quality. And I'll tell you right now, take a look at this on your laptop when I post the slides later. It does a much better job than the projector here. But so in the top left corner, we've got JPEG just at 80% quality. So that's not even the best JPEG that we can get. And that looks, at least to the human eye, maybe not so much on the projector, like a pretty good picture of a parakeet. Okay? Now, all of the other images are what's a PNG image, which is a different type of image format, where there's sort of a lot more dials and levers that we can crank to sort of play with the quality of the image. And so here, you know, this is now using PNG 24. Notice it's got 16 and some odd million colors. Where do you think those come from? That's RGB. Okay, because remember we saw there were about 16.5 million colors thereabout. And notice the file size actually increased quite a bit from 14.7 kilobytes to up to almost 54 kilobytes. And again, the human eye doesn't really notice the difference. If we come in, and now we have a reduced quality PNG, only 256 colors, again, do you really notice much difference between those two images? Not really. Okay, so we can reduce it even more down to 128 colors. Do you notice a big difference between these two? Not really. Coming down to 64 colors, big difference? Not really. 32 colors. On the projector, you're probably not noticing much of a difference, but on your laptop screen, you might start to see a little bit. Even 16 colors is not bad. 8 colors. Okay, so if you look sort of down here where there was a lot of contrast before, you're noticing you're starting to get some degradation down in the bird's chest. 4 colors, okay, that's now noticeably not good. And 2 colors where we now have each pixel is either black or white. I don't know if that looks like a bird or just some really bad microscope of some really weird organism that's zoomed in really, really close. Okay, but the idea is there's all these different styles of file formats, and there's these different levers and, like I said, knobs you can twist to try to figure out what's the right file size, what's the right resolution to make the image appropriate for viewing. And in a lot of cases, the human eye will fill in the details. Okay, so then to sort of put it all together and end our data storage unit, to put it all together, I mean, this is basically everything you have. All of these documents that we have, whether it's an image, whether it's text, a Word document, spreadsheet, web page, we can find ways to turn all of these quantities into ones and zeros. If it's numbers, just use the binary number system, or one of the variants we've discussed. If it's text, use one of these encoding strategies like the ASCII table. There are more sophisticated ways, like in the rich text format, or if anyone's used an RTF file, they're a little bit more sophisticated, and so it adds information beyond the text that says what's the font that we're using, maybe what's the color of the text. Is it bolded or italicized or underlined? And they're all flags that we can introduce in the binary, in the ones and zeros of the file that tell the computer, know that this text is boldface and 32 size font. Word documents, whether the original .doc or the more recent .docx, are even more sophisticated. They allow you to embed images. They give you more control over layout. You can set margins. Word is what's called a WYSIWYG. Has anyone heard that acronym before? Stands for what you see is what you get, where you can look at the document in Word, and when you print it out, you basically get what it looks like. There are other formats that are not WYSIWYGs. PDF files work in a very similar way. And the idea here is that they've now sort of standardized how do we represent these documents. Unlike a Word file, are PDF files generally editable? No, they're usually read-only. And that's what makes PDF files work. Does anybody know? Well, I'll give you the description right there. PDF stands for Portable Document Format. And the reason for that, why they made them read-only, is they can then guarantee everything subscribes to this one standard form. And so when you take your PDF from one computer to another computer, there's no degradation. And if you send, so for instance, you submit a PDF file to us on Blackboard. By using PDF, we can guarantee that the file is going to look the same on your computer as it's going to look on my computer. Can you necessarily guarantee that with a Word document? No, you can't. Microsoft has spent a lot of money trying to fix this problem, so Word documents are usually pretty portable unless you're doing something really weird or sophisticated in the document, but it's not guaranteed. Okay? Versus a PDF, that is the guarantee. That was the goal of PDF when Acrobat and Adobe introduced them 20, 25 years ago. And so then all of these other objects, whether we wanted spreadsheets, presentations, music, videos, all build on these ideas. If it's text or a number, we can convert it easily. If it's something more sophisticated, can we somehow discretize what we have up and then develop a standard by which we can store all of those ones and zeros? And that's what's going on. So does anybody have any questions about this before we sort of jump ship and move into the next unit? What was that? Yeah, can we keep this up for a minute? Sure. And again, it'll be posted after class. Exactly. So the question was, is this sort of how YouTube video resolution works? And yeah, so if you lower the resolution, then you're degrading the quality of the video, but you're making the video smaller, which means it takes less time for it to get across the internet to you. It takes less time for your computer to process it, but again, you're degrading the quality. And so there's always this trade-off of, well, we can always add more quality, but then it requires more compute time. And so long as you can view the video in real time, and you as the human are not really noticing any degradation, are you going to care? No, and that's the trade-off, is figuring out where is that limit and what's that balance. Yep. Okay, we good? All right. So let us now move into our next unit. So we're going to continue this idea of digital devices. We're going to have 3 units in total on this. We're going to start the second unit on that now. Where before we were looking at sort of data storage, now we're going to sort of move into data transmission. So this is just a summary of what we had in the last time. With the idea that data storage is great, so it says here's how we store this information on one computer. Here's how we process this information on one computer. But as you know, do we necessarily want to keep that data exactly on one computer? No. Sometimes we want to transfer it. You want to turn in your homework assignment so that we can grade it. That requires transferring the data from your computer or your device to Blackboard servers to our computers where we can actually grade them. And so one of the other key things that we're going to have to discuss when thinking about how do these digital devices working, or how do they work, is how do we get the data from one device to another? And that's the theme of this unit. So thinking back to why this is important, what are different types of operations that we do where you need to transfer data? We've already mentioned one of you turning in homework or assignments. What are other times you're using computers or other devices to transfer data? Yep. Okay, so doing money, you can do online banking. There's absolutely information going back and forth between your computer and the bank servers to do that. Yep.
Sending emails.
So sending emails, absolutely. Text messaging, great example. Okay, so online commerce. If you've got some sort of music sales where they can then send you the money and you can send them the music file, like if you go through, I don't know, was it Google Play? Something like that? Or iTunes or the Apple Store, or whatever the case may be. Okay. We've also mentioned, we had YouTube. Is there data transfer involved in YouTube? Yeah, because you're going to go to the website and say, I need this video, and they're going to send you the data back so that you can view it on your computer. So there are all sorts. If you want to get a little bit more old school, fax machines were one way of doing data transfer. Has anybody here actually used a fax machine? Oh, more than I expected. Okay. The internet itself is big data transfer, where we've got, one computer here and another computer somewhere else, and we're transferring data. We'll come back to that point much later in the semester. Voice over internet protocol, who's used Skype or something similar? Is there data transfer going on there? Yeah, so there's all sorts of different applications where we're looking at data transfer. So again, sort of stepping back and looking historically, before we maybe had all of these computers and these sophisticated devices, what are different ways that we've used as a civilization or as a culture to do data transfer? 2 cans and a string. I love it. Has anybody, when you were like a little kid, done that where you took the 2 soup cans, put a string, and you could sort of talk into the can and you could hear it on the other end? Or did you just see that done on cartoons and think, oh, that's kind of cool and screw it? Okay. So that's certainly maybe one way. It's a bit of a joke, but it would certainly work. What are some other ways we use for data transfer? We could use a telegraph or the post system. I mean, you've written a letter, you put it in the envelope, you look at, you remember to put the stamp on it, the address, you put your return address, and you hand it to the mail delivery person, and they take it somewhere. Does that transfer data? Sure. It's not necessarily digital data, but it's data nonetheless. Other ideas? Okay, communication in general. I am here talking to you, and we're talking about data transmission. Am I transmitting data to you about data transmission? Yes, I am. So there's a whole bunch of different things. So language in the spoken word is probably the most fundamental way right now of doing data transmission, whether that's orally or written, are two different ways. What was that? Our brains are full of data. They're one big data storage thing, only it's probably not digital. Go take some neuroscience classes if you want to learn how the brain stores data, and I think the consensus is they don't entirely know. Okay, but we've already mentioned mail. We have telephones. Again, sort of building on the spoken word, but now introducing a little bit more modern technology. Smoke signals could be one way of transmitting data. There are certainly plenty of others. Anybody think of again, any other ways now that we've got sort of our brains going a little bit? Okay. Well, if you do, let me know. We can add that. So what are the limitations of some of these things? Why did we say the post office wasn't good enough? Why did we say telephones weren't good enough? Why did we say the spoken word isn't good enough? Well, some of the limitations might be range of service. Okay? If I turn off my microphone, in the front, they could hear what I'm saying, maybe. If I talked real soft, maybe not. But those of you in the back probably didn't even notice I was talking other than my lips were moving. Okay, so there's a range of service. If we're going to make this work, we've got to make sure I'm using the microphone so that everyone can hear. But if I'm using the microphone in this room, is someone in Patchogue going to hear this lecture? Probably not. So there could be proximity effects. Okay? What about the delivery speed? Does that sometimes make a difference? Okay, right now, we're all close enough in this room and there are the speakers around that it's basically instantaneous transmission. But is that always the case? If you put a letter in the mail, does that person receive it instantaneously? No, it usually takes a couple days. Is this necessarily important? Yeah. So one story is sort of a historical aside. If you go back and look at the presidential election of 1800, back 200 odd years ago, John Adams was the incumbent president running for re-election. He was defeated by Vice President Jefferson. But one of the big issues at that time was what's going on in this France quasi-war. So France was in the middle of its revolution when this election was happening. Adams said, I'd love to get involved and help the French. Remember, the French were a big ally of America in our recently fought Revolutionary War at that point. We would love to get in and help France, but we have no navy, or a very small navy. We have no money, and we're still trying to figure out what exactly are we now that we've gotten rid of Great Britain. And we just don't have the resources to get involved. Jefferson, on the other hand, said, the French were our allies and they helped us out. We need to go help them. And we need to give everything we can to do this. And this was one of the most contentious issues in that election. So Adams, being the president, kept running everything saying, we're not getting involved, we're not getting involved, we're not getting involved. And the election happens and Jefferson wins. Okay. The issue that happened is the French Revolution actually ended between when we held our election and when the electors for the Electoral College actually voted a month later in December. And France, the rebels won. They overthrew King Louis. They put in this really big revolutionary known as Bonaparte. And we all know how that worked out. But anyway, they send message and they send a courier back to America in early November of 1800 saying, the French Revolution is over. We know you couldn't get involved. You're a new country. You don't have a lot of resources. We don't blame you. We still stand by you and we're glad to be your friends. And it takes how long for that message to come across the Atlantic Ocean? Probably about a month and a half. So by the time the message actually gets to America, the electors have actually voted saying, Thomas Jefferson's right, we've got to help the French, this is a big issue, to realize, oh, everything was determined a month ago. And did that have an impact on the election? Quite conceivably it did. I mean, it's hard to go back and say, well, if we'd had more instantaneous communications, Adams would have been reelected. I don't know. But that can have huge consequences, that idea of delivery speed. Is message reliability an issue? Yeah. Is it possible that messages can get garbled in transmission? Has anybody ever gotten it when you, from the post office, you'll get your letter and it's in the little like plastic bag with the, oops, sorry, your thing got jammed in our machine and your whole half of your letter is sort of like crushed up and torn because it got stuck in the mail sorter? Has that happened to anyone? Okay, it's happened to me, but messages can get garbled. And then the other item, which I'll mention now, but this will be the focus of our next unit that will start in about 2 weeks, is the idea of security. Do we necessarily care whether our message or our communication is secure? Yeah, conceivably we might. So on that note, does anybody know what the picture is on this slide? It's not a typewriter. It is not a telegraph. I mean, yes, it is. It's like a typewriter. It's like a telegraph, but that's not specifically what it is. Going back for more historical context, it is the Enigma machine. Has anybody heard of the Enigma machine? Okay, what was it used for?
So the Enigma machine was the machine that Germany used to encrypt their messages. It
Yep.
was basically thought to be unbreakable until I think, was it Turing? Turing and his team in Great Britain worked on it and they figured out a way to break it. But until then, it was the way that they sent submarine machines.
Right. So in short, you're giving the Allies way too much credit for breaking these things. To recap what you said, just on the microphone so everyone can hear it, this is the Enigma machine, which was a device developed by the Axis powers in World War II to have secure communications. And this stumped the crud out of the Allies because it was a very good cryptography system. Axis powers would take whatever message they had, encrypt it using the Enigma machine. They could then transmit it any way they wanted. Get it to the receiver. They would then use another Enigma machine to decrypt it and look at what the messages were. And the Allies had absolutely no idea how to decrypt it. Your comment was, well, maybe Turing and them figured out a way to do it. No, they didn't. What actually happened was in one of the raids, the Axis people were not quick enough in destroying their Enigma machine, and the Allies intercepted one of the machines. One of the things that the Axis powers did then was, if you're going to lose a battle or lose a thing, the first thing you do is destroy the Enigma machine. And they weren't quick enough to do it. The Allies then got lucky where they weren't able to actually tell the Axis powers that the one got captured. And so there's about a 2-year period where the Allies powers were able to actually intercept and decrypt the messages without the Axis powers knowing. But so data security can again have major, major implications worldwide. Go ahead.
And the only reason they were ever able to figure out what it did was because they managed to get the German army to send them the same message twice, and because the letter could never represent itself.
Right.
Right.
And so there were other things once they had the device that allowed them to decrypt it without the Germans knowing. Anyway, so one of the main themes of the unit that we're going to discuss now is dealing with this idea of reliability of data transmission. So suppose you text your mom, I hate this 8:30 a.m. class, the prof is totes boring. Yes, I'm old and I know slang. What I'm more impressed is that you use the semicolon, which is the proper punctuation at that point. How do you know your mom gets this message correctly? Okay, so your phone says delivered, but you see that message. Does that still tell you your mom got the message correctly? How do you know? How do you know your mom got that message? Okay, so she responds back. Okay, but even then, are you still entirely sure? Because what if she says, oh, that's great. Are you sure she got the right message? How do you, maybe she didn't get the message, I love this 8:30 a.m. class, the prof is totes cool. And again, comments that you use the semicolon, good for you. Yeah. Okay, so the most robust way to do this would be at some point later, you look at her phone, and you can go look in the log and see that she did in fact get the right message. Is that a particularly good way of ensuring data reliability? No, because if you had access to her phone, would you be using text messages? Probably not. You would just tell her, oh, I hate this 8:30 a.m. class. Okay? And so this is sort of one of the themes that we're going to try to get at as we go through this unit, is how do we know or guarantee that the message received is identical to the message that's sent? And there are a couple facets of this problem that we're going to have to discuss. One of them is, you might ask yourselves, is this really a problem? How likely is it that a message doesn't get reliably transmitted? If it doesn't really occur all that often, do we really have to worry about this? Or am I just making hay out of nothing? Okay. So bear with me, and you'll probably be guessing that the fact that I'm asking this question, it is a problem. We'll come back to that momentarily. But so if it's a problem, what can we do about it? How do we actually try to develop tools that allow us to know that this data was transmitted reliably? Okay, and those are going to be sort of the two themes for this unit. So what I'd like to do now is we can play a quick game, and I need, let's say between 10 and 15 volunteers. If anyone wants to just come down to the front. I promise it won't hurt. What was that? No, I need people to actually be up here because I need you to stand in a line at the front. So if 10 or 15 people want to come up, just come on up. You don't have to raise your hand. We're going to bring back maybe shades of elementary school here. Does anybody remember playing either the telegram game or the telephone game or whatnot? Okay, we need more volunteers in this. I think there's still a reasonable chance these people will be honest and not screw up the message. Okay, so the idea here is we're going to have this line, and let's see, so who's down at the end now? So down at the end, your name is? Nick. So I'm going to send Nick a message, but the only way to send it is I have to whisper it to Mike, who whispers it to Tyler, and so on and so forth until it gets down to Nick. What do you think is the likelihood that this message is going to get through well? It's probably not likely. I'm going to assume none of you are nefarious and going to intentionally screw it up, but maybe one of you might. On the other hand, maybe there's just going to be error in the way. So what I'm going to do now is whisper the message to Mike, and we'll see how well we do. Okay, so what do you think the message is?
I don't know, something about shoes?
Okay, I don't know something about shoes. Is that what it started with? No. Okay, so first of all, thank you everyone for the demo. So the message that we started with was, mines are like parachutes. Just because you've lost yours doesn't mean you can borrow mine. Okay, so we got line. I think we know where shoes came from because shoots got garbled. Okay. But so the idea here is, even with just 10 people, and I realize we had a little bit less than 10 people here, the message got degraded going through the chain. So I'm going to guess by the fact that we actually got something like shoes out at the end, no one actually deliberately tried to mangle the message, although maybe one of you might. I don't know, are you willing to volunteer? Did you intentionally mangle it? You couldn't hear it, good enough. Okay, so there are lots of different ways. Some of it is just there's transmission error. Every time one person whispered the message to the next person, there was a chance there was going to be an error, and that just happens. Maybe there was the chance that someone was just being nefarious. I don't know. But so the idea here is for some terminology to introduce. When we're thinking about data transmission, what we're looking at are what are called channels. So a channel is any medium or any way of transmitting data. So there was a channel of, about our 8 people from me to Nick that were transmitting this message along. Okay? So it's just, a channel is just some path or some way that our message goes from source to destination. And then there's 2 different types of channels in particular that we're interested in working with. One is a lossless channel, which is to say a lossless channel will transmit the message with perfect fidelity. What does that mean? Errors can never get introduced. Was our telephone game a lossless channel? No. We had at least one error. Okay? And so then conversely, if our channel isn't lossless, we'll call it a lossy channel, meaning there is the potential that errors could be introduced. Now, for a moment to build on this a little bit, is it guaranteed that a lossy channel will introduce an error? No. The message might get through completely unaltered through a lossy channel, but the idea is we can't guarantee that. It may be very unlikely that an error gets through, but it could still very well be possible. Okay? So, the bad news is lossless channels are a myth. They don't exist. Outside of an academic setting in an early level course, we'll say just don't worry about this problem. In reality, every channel is lossy. Okay? So let's figure out, does this matter? So suppose we're not going to take out our phones and we're going to take a picture, and you have a 3 megabyte picture. Okay, so megabyte is roughly how many bits? Remember, mega was the prefix for million, so it's 1024 squared bits. Okay? And so you want to take this picture of about 3 million pixels, or 3 million bits, and you want to send it to your BFF. Okay? Suppose now, as we're sending this message through in our text messaging channel, that there's a 99.99% chance that every bit gets transmitted correctly. Okay, so which is to say there's a 0.01 chance that any bit gets mangled. What is the chance that your BFF receives the correct, 100% correct message? We'll talk about how to actually calculate this number next time, but I'm just going to, does anybody want to take a guess? Do you think your BFF is going to get the picture? You would hope. That's not the question we're asking, though. Anybody want to take a guess? What's the probability? Okay, so you're saying there's a pretty good chance they're going to get the image. Almost 100% chance they'll get the image. Okay, anybody want to take another guess? 100% chance, almost 0. Okay, so we've now got the two sides. We've got one person saying almost 100% and another person saying almost 0% chance. Okay, so the answer is about 10 to the minus 1093. Which is to say you probably have a better chance of winning the lotto jackpot every day for the rest of your life than you would for this picture ever once getting transmitted correctly. Okay? So, where did this come from? The idea is every time there's a bit, okay, so we transmit our first bit. What's the chance that it gets successfully transmitted? 99.99%. Okay. So suppose that does get transmitted correctly. Now we have our second bit. What's the chance that gets transmitted correctly? 99.99%. So every one of these bits, there's that 0.01 chance that it can go wrong. And when you compound that over 3 million bits, does 0.01% chance start to seem that unreasonable when you're talking about 3 million? No, it doesn't. And so, like I said, we'll talk about where this number came from on the next lecture. But another question we might then ask, since we know now it's practically impossible that this image is going to get through, how many errors would we expect during the time where we're sending that message? So now we have these 3 million approximately bits. How many of them do we expect to be wrong, knowing that the channel transmits each bit with a 99.99% success rate? Mm-hmm. Yep. Okay. Okay. So I think your idea is right. We might want to check the work a little bit. Okay. But what ends up happening, and again, we'll talk about where this number comes from on Monday, but about 2,500. So we would expect 2,500 of those bits to get garbled in this line. And so now here's the rub. Here we said this channel, it's a lossy channel for sure, but there's a 99.99% chance that every bit is transmitted correctly, and this is a massive problem. Do you think in reality the channels that we're actually using for text messaging are as good as 99.99% accurate? Probably not. I have no reason to say this, but I would be willing to bet it's considerably less than that. Engineering purposes and like doing Wi-Fi communications, I'm sort of from various comments I've heard from people that work in computer networking, I would be willing to believe probably 75% is really, really good. Okay, so in reality, the problem is even worse than what we had in this sort of sample problem. So to come back to our question, is this idea of data reliability a problem? Yes, it is. This is something we have to deal with. And the good news is the engineers and mathematicians and scientists have actually done a pretty good job of dealing with it, because when you send your picture over text messaging to your BFF, does your BFF get it? Usually. So somehow we figured out a way to work with this and to deal with it. And that's what we're going to be discussing. So any ideas then? So all channels are lossy, and lossy channels are problematic. How might we go about dealing with this type of reliability issue? Any thoughts? If you know a message gets messed up, what might you do to try to fix it? Okay, so you could go back to the sender and say, hey, that got garbled, can you send it again? Is that a viable approach? Sure. In most cases. It may not always be what you want, but it's at least conceptually, theoretically, that would work just fine. Yep. Can you simplify the message and maybe make it shorter? Okay. If there are fewer bits to send, we expect fewer errors. Okay. What was that? It might get there faster too. That's also a possibility. Yeah. Okay, try to fix the medium that travels through. No one's ever given me that answer before. I like that. We're not going to be able to do much about that in this unit, but I think that's a great idea. So we go to the engineers and say, make it better. Okay? So there are a couple things. We've said resend the message. Could you add redundancy? Maybe just in the message, rather than saying you have to resend it, just send every bit twice or 3 times. And you could sort of compare and try to identify, were there errors? Okay? And so one of the ideas is, if we were to add this redundancy, can that help us detect, did an error happen? So maybe we can say, oh, well, this message, as it turns out, didn't have an error. There's no reason to resend it. Versus using this data, oh, this message did have an error. Please resend. Okay? The other thing that we might do is, rather than just adding just redundancy, is actually add some extra data to the message. And why might we want to do this? Because we just said shorter messages are better, so why would we want to lengthen our message with some extra stuff? If we add actual data more than just redundancy, if we add a little bit more context, not only could we detect the error, but it's possible we could actually just correct it. And so in that case, the receiver says, here's this message, oh, there was an error, but because of that extra data, I just know how to correct it. I can determine what the original message was. There's no need to resend it. Everything's good. Okay? And so that's going to be what we talk about the end of next week, is how do we deal with these different, what are called either error detecting or error correcting codes that we can use to help with this data transmission. Okay. And so for one instance, so there was the movie that came out about 1.5 years ago. I don't know if anyone saw it, with Tina Fey, the Whiskey Tango Foxtrot. Does anybody know why it was called that? Or where the name came from? Okay, so notice that the first letter of whiskey is W, and then there's a T, and there's an F, and ha-ha. Does anybody know what those Whiskey Tango Foxtrot are called more generally? It's not necessarily military code. It was developed by NATO, but it's not necessarily for the military. What it's called is a phonetic alphabet. And so this is exactly that idea of, let's add redundancy to our data. So we could say Whiskey Tango Foxtrot. Okay, we could say WTF, but it's possible that would get garbled. Because does T sound like other letters in the alphabet? If we knew they were just letters, does T sound like B, or D, or C, or E, or G, or V, or P? Okay, there are lots of letters. And so if maybe the beginning, we're transmitting now this oral data, if the beginning of that syllable gets lopped off, they all sound like E. Is that problematic? Potentially. And so what they developed when they were doing radio communications was this idea of a phonetic alphabet, where rather than saying the actual letter, like A, B, C, D, or E, we put a word associated with it. So like B becomes Bravo, C becomes Charlie. You've probably seen this if you've watched several TV shows. Okay? With the idea, if you look at all 26 of them, no 2 of these words in their entirety sound alike. The only word on there that sounds like November is November. So if you get the message, Ember, you can know, oh, well, that had to be November. That's the only possible thing it could have been. That must be an N. Now, does that Ovember actually add anything to our message? No, we're still just saying N, but we've added that extra bit of data to help the receiver detect and, in this case, correct any errors that occurred in the transmission. And so this is one fairly simple type of what might be called an error-correcting code. Yep? Okay. Okay, so the comment was this is actually still fairly common and used in countries that don't have good telephone systems. Yep, I believe that. Yep. So how are they determined? Some person probably just sat down and started putting words together and then just make sure that none of the two sound alike. I mean, by no means is this a unique set. This is just the one that's become, again, it's a standard. If you don't like it, make another standard, and there's two competing standards. Okay, so like I said, the phonetic alphabet exemplifies an error-correcting code. And so the idea of this more generally is we've added this extra data in our message. That data doesn't actually transmit any information. By adding that Ovember, we didn't add anything. There's no new information, but it does help the receiver correct the error. And so our driving question as we sort of move through this, as we said a little while ago, is how do we know or guarantee that the message received is identical to the message sent? Okay, that the receiver got what we were trying to send them. And the two math tools we'll need, one, we're going to need to look at a little bit of probability and statistics, where we can try to determine what's the impact of a lossy channel. Okay, because maybe if the channel's mostly pretty good, that might lead us to a different problem-solving technique than if the channel's really cruddy. Okay, if we can understand how many errors do we expect we're going to get in a message, that can help us and help guide us to determine how do we correct for that, how do we account for that. And then what we'll do is we need to bring in a little bit of what's called information theory, and this will be more next Wednesday, to examine the efficiency of these error detecting and error correcting codes to then try to find what's the right one for the particular channel we have at hand. Once we've tried to identify how many errors should we be expecting when we do a message. Okay? Any questions on that? So then, what I would like you to do is to please put your pens or put your notebooks away, put your calculators away, because we're going to have a pop quiz. Oh, stop glaring at me. Okay, so please keep the quiz face down. Actually, I guess it doesn't really matter. You can turn it face up if you want and start putting your name and ID on the top. That's fine. And if you've got extra sheets in your row, just please hand them back. See, aren't you glad you got up this morning now? Mm-hmm. So do you think this is a real quiz? No. What's the purpose of this? Okay, so well, first of all, it's an attendance mechanism. Ha 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 ha. See, but I had you all, I got your blood, I got your hearts pumping there for a moment. But the second thing is, we're going to do an experiment. Okay, so what we're going to see is some statistics next time. How many questions, so you have to randomly guess on all of these. Okay? How many do you think you're going to get right? Okay, 1, 0, 3. Okay, well, so what I'm looking is I want to gather a data set now from your quizzes, and we're going to look at this next time and see what happens. So please, just guess on every question. Do not just put all true or all false. That's boring. Don't just go true, false, true, false, true, false. That's also boring. Okay? When you're done, just hand them in. That'll be it for today. Have a wonderful weekend, and I will see you on Monday.